Hello students, welcome back. Now we went through section 1 and then section 2 as an optional topic and section 3, but as a matter of fact all those were review. We took several weeks to go through all these in algebra classes, whether you took STEM algebra or business algebra or algebra for teachers. I just covered all those very quickly, several weeks of materials in I don't know, maybe 1 hour or 1.5 hours, probably less. But in any case, let's say those are all done, and if you need further review, go ahead and review yourself. Now let's go to section 4, derivatives of exponential and logarithmic functions. This is not completely new either, as a matter of fact, because we have been using the derivative formulas for exponential and logarithmic functions. Here we go. Derivative of natural exponential function is itself. The derivative of natural logarithmic function is 1 over x, or equivalently speaking, x to the negative first power. Either way, whatever is more convenient for you. Me personally, I find the power form more convenient. I like this one better. But our textbook author does it this way. That's okay too. Now these we already discussed, and then I slipped in these functions here and there in the derivative computations already, and then tangent line computations and things like those already. Now these we didn't cover yet, so let's talk about these. The derivative formula for a to the x power is a to the x power times log of a, natural log of a. The derivative of log base a of x is 1 over x times log of a, or equivalently speaking, 1 over natural log of a times x to the negative first power. Which form do I prefer? I prefer the power form. This one. I prefer this one. But of course, our textbook author prefers this one, obviously. They're the same. Now, why is that? Well, you can do this computation like this, and that is that the derivative of exponential of x natural log of a by the change of base formula. Okay, all right. So if you apply the derivative rule for exponential function, it stays the same, right? And then by chain rule, I have to multiply the derivative of the inside. Derivative of x times something, where the coefficient is a derivative, that's log of a. And then now what is this? E to the x log of a, that's a to the x back. So we get a to the x power times log of a. That's how you get this formula there. And then how about this formula here? Log base a of x. Oops, log base a of x is the derivative natural log of x. Let me copy and paste all these. Natural log of x over natural log of a by the change of base formula. All right, 1 over log of a, that's coefficient, so stay the same. And the derivative of 1 over x is, derivative of log of x is 1 over x. Therefore, you get 1 over x times log of a. In short, these formulae are not really necessary. If you have to do the derivative computation for, say, for example, 3 to the x power, changes into natural exponential function like this, and then apply the derivative rule for exponential function, the natural exponential function, like this. And then there's no need for simplification, and you can stop there. For instance, there's a reason I did not emphasize these before, because they follow immediately from the original, just by chain rule. Let's see, do we have some example problems here? Okay, let's go ahead and do some of these. Looks like this is a product rule problem. We took the first exam, we took the midterm exam recently, so I hope everybody remembers. Yes? No? I hope everybody does. U prime, the derivative of the first function, plus the second function, and then the first function u, times the derivative of the second function. Remember that? U prime v plus uv prime. This is u prime, and then v, and this is u, there's v prime. Now what is u prime? The derivative of the first function. Let's go ahead and do that. 2x plus exponential function stay the same. Now how about this? Derivative of the second. Derivative of 1 is, that's 0, so I don't have to do anything. And derivative of this log function is 1 over x. And there's a product rule. And I don't think you need to simplify it. Let's just stop here. Let's see, what did I do here in my answer key? Yep, the very same thing. No need to simplify. So natural exponential and natural log, you know how to deal with those. Now how about another product rule, but then again looks like we have a composite function, so we need some chain rule as well. Okay, that looks a bit more challenging. U prime v and then u v prime. Do you like the structure here? Structure of the outside first. Outer structure is product, so product rule first. U prime v plus uv prime. This part and that part are nothing more than just copy and pasting. Now I have to take the derivative here for this function, and then derivative here for the second function. Make sense? Okay, let's go ahead and complete this problem. Copy and paste this part. Okay, here let's do the derivative computation. Derivative of x squared is 2x, so far so good. Exponential function stay the same, so far so good. And by the chain rule, we have to multiply the derivative of the inside. What is it? That's 2. Does it make sense? And of course, it's customary to write 2 on the left-hand side. So if you rewrite like this, your final answer will look a little bit better. But of course, that kind of, that's kind of modification is not really required for my class. Okay, let's look at this. Log function. So it's 1 over x, but instead of x, I have 1 plus x squared. So that one goes to denominator, and we have to apply the chain rule. Multiply the derivative of the inside. What is it? Derivative of 1 is 0. Derivative of x squared is 2x. All right? And the derivative of this 5 is 5. And that completes the problem. Oops. Now this 2x, you can write like this, but most of the time it's better this way. Multiplying goes to the numerator, so multiply like this. And this form is a little bit better. But the previous form is correct as well. So it's just a derivative computation, which we are already familiar with, but we're using the product rules and chain rules to exponential and logarithmic functions. Using product rule, no big deal. chain rules can be tricky, especially to the log functions. Somehow this multiplication going to numerator, many students are somehow getting intimidated by that. I don't know why, but it should not be that intimidating, but that's happening many times. How about this one? This one looks like a quotient rule problem. You can stop the playback and go ahead. So denominator squared, and then I need u prime v minus u v prime, and then this v and u, they are just copy and pasting, and here I need the derivative of the numerator, here I need the derivative of the denominator, and each of them requires multiple uses of chain rule. Exponential stay the same and multiply the derivative of inside, that's 2. Exponential stay the same, multiply the derivative of the inside, that's -3. Exponential stay the same and multiply the derivative of the inside, that's -2. And that's how we get this. And then similarly we get that. And then if you simplify, somehow you're going to get this. And that's one way to handle it. But other ways to handle those are kind of like this. You can separate the numerator like this, simplify. That's not the end of the problem, it's just simplification. And then you take the derivative term by term. This derivative, that becomes 0. This derivative and this derivative, by chain rule, we get -5 and -4. Which is easier? To me, the separation method is easier than using the quotient rule. But you can use quotient rule if you want. But I do like this first rule. Separate the numerator, simplify, and then take the derivative, because this one is effective for calculating the antiderivative as well. We're going to do backward computation later on, anti-differentiation. In that sense, this is really useful. Here's another way. Instead of separating the numerator, flip the denominator over and then distribute through multiplication. In the end, of course, you have to get the same thing. And then you can take the derivative term by term. Okay, all right. I do not want to overemphasize these at this moment. But this one, everybody should be familiar, the quotient rule. We'll revisit this kind of problem when we deal with antiderivatives. For now, let's keep it at that, and let's see, do we have enough time for an example problem here? Oh, maybe not, so let's stop here. We did some derivative computation, which two are mostly review as a matter of fact. All right.